Hello, I'm Napollion. I work under Dr. Kwon Kim in the Department of Mechanical Engineering. My work goes over the effect of temperature on the electrochemical properties of ionic polymer metal composite, or Ipmc capacitors. The primary goal of this study is to explore the electrochemical characteristics of platinum-based Ipmc capacitors. To also design the shape and structure of flexible capacitors following conventional working mechanism where the dielectric or polymer is sandwiched between two electrodes. Capacitor developed in this study could be used for applications for medical and military where high temperatures are often the standard or required. So, what is our objective of our study? To develop an understanding of the structural and chemical bonding of the polymer and the interactions between the polymer and the electrodes. In order to do that, we design and fabricate the shape and structure of flexible capacitors following conventional working mechanism where the polymer is sandwiched between two platinum electrodes. Study and characterize the electrochemical performance of the flexible Ipmc capacitors. Based on the results, we then improve and optimize the electrochemical performance of these capacitors. Just to give a little background on Ipmcs, Ipmcs are a type of electroactive polymers or EAPs, which means they display change in sizes and shapes once electric field or voltage is applied. They have become important in the study of actuators and sensors. The polymer, which is made of Napollion, is plated on both sides with noble metals such as platinum or gold electrodes. Platinum and gold are used due to their chemical stability and low electric resistivity. The electrodes are deposited through the impregnation reduction process. This process can cause the Ipmc to have different textures since the user has poor control over the surface characteristics of the electrodes. Ipmcs are excellent candidates for underwater and biomimetic robotics as they are composed of soft and flexible structure. They require low driving voltage and able to operate in aqueous environments. Conventional capacitors are restricted by sizes, shapes, and typically occupy the space that they are put in. Ionic polymer metal composite capacitors, however, they can be fabricated to any planar shapes and sizes in order to meet the needs of specific applications. The thickness of the polymer is at micron level, which reduces the weight of the cell and allow the system to be lighter, safer, and flexible. Research is being conducted of an Ipmc for use of catheter in order to diagnose or treat heart conditions. Ipmc has advantages such as low driving voltage, flexibility, and no moving parts, making the material desirable for use in medical devices. A low driving voltage is important in meeting electrical standards. Flexibility of the polymer allows to be used for implantable medical devices. Not having moving parts reduce the risk of irritation of the surrounding tissue. Ipmc is biocompatible and the Ipmc samples have been tested for toxicity and passed the ISO 10993 testings. While Ipmc characteristics make the material desirable for use in medical devices, there are many areas that require further development before Ipmc is ready for medical applications. Mechanical testing has been conducted in the past, and they are currently being conducted. For this study, we go through the electrochemical characterization of Ipmc due to temperature. Many factors affect the dynamics of ion mobility in Ipmc. The mean free path of ions, which is a factor of membrane thickness, and membrane's chemical and physical structures. Characteristics of ions, which follows the van der Waals volume, and temperature. While characteristics of the membrane and ions are intrinsic to Ipmcs and they are fixed, temperature is considered an external factor that can be changed. Therefore, understanding the effect of temperature on Ipmc is important in the prediction of the electrochemical behavior under different environmental conditions. Increasing temperature will expand Napollion's nanochannels and increases the kinetic energy of the clusters. Benziger's paper talked about how elastic modulus of Napollon decreased with increasing temperature. The free volume increases with increasing temperature as the nanochannel expands. We're also considering the glass transition temperature of Napollon occurring between 55 and 130 degrees Celsius, where Napollon becomes rubbery, which affects the ion transport properties within the nanochannels. The cyclic voltammetry and the electroimpedance spectroscopy or EIS measurements were conducted to investigate the electrochemical properties of the Ipmcs. Measurements were performed at room temperature to 90 degrees Celsius in deionized water. Morphology of the sample was conducted using a scanning electron microscope or SEM, which presents cracks in the whole surface of the platinum electrodes. The platinum electrodes are deposited through the impregnation reduction process. This process can cause the Ipmc to have different textures. SEM results might show a small separation between the electrodes and the polymer. The separation allows for charges to accumulate at the interface between the electrodes and the polymer, forming double layer. In order to examine and investigate the distribution of the platinum electrodes onto the membrane or polymer, an X-ray diffraction analysis was carried out. The result shows that the platinum particles membrane have penetrated deep into the polymer membrane. The electrochemical phenomena of the electrode surface of the platinum Ipmc is essential factor when interpreting the fundamental characteristics of the Ipmc. Based on the principle of Ipmc actuators, a chemical reaction on the cathode surface is expected to affect the deformation properties. This is due to when a small amount of voltage is applied across the electrode, the cations bind with water molecules, generating a higher density of water molecules on one side of the membrane, converting the electrical potential into mechanical work through actuation. As shown here, oxidation and reduction peaks become prominent with increase in temperature. Cyclic voltammetry obtained at different temperatures showed an increase in the hysteresis with increase in temperature. Electrical resistance increases with decreasing temperature, which increases the Ipmc conductivity. We have here the time-dependent current flow measured at different temperatures in deionized water. The result shows that the current flow across the polymer membrane increases with increase in temperature. The electrochemical behavior followed a constant pattern until 55 degrees Celsius. Then a drop is seen at 55 degrees Celsius. This might be due to the glass transition temperature of Ipmc starting at 55 degrees Celsius, where Napollon becomes rubbery. The structure of the membrane and ion transportation properties are affected. For charging and discharging, when voltage is applied, Ipmc displays the charging and discharging effects of a capacitor. For the capacitance measurement, on top here we have a capacitance as a function of frequency. One thing to notice here is capacitance decreases as frequency is increased. Capacitance drops at 55 degrees Celsius and increases right after. This might be due to the glass transition temperature mentioned in the previous slide. High current flow capacitance at a 90 degrees Celsius indicates physical or chemical degradation. For the electrochemical impedance spectroscopy, as temperature of the solution increases, the mobility of the ions also increases, which increases its conductivity. The equivalent RC electrical circuit was used in order to fit the experimental Nyquist data. The irregular behavior of the Ipmcs at higher temperature shown here might be due to the changes in Napollion's nanostructure as the nanostructure expands with increasing temperature. This will cause the change in ion transportation through Napollon. Ionic conductivity tells us about the movement of ions. From the plot, we can conclude that conductivity increased with temperature. A different conductivity behavior was noticed for temperature range between 21 to 60 degrees Celsius, then temperature from 60 to 80 degrees Celsius after feeding the conductivity data with the Arrhenius equation shown here. Our study shows for temperature greater than 60 degrees Celsius, the experimental data matches the model, which means that there is no breakage between the nanochannels. In conclusion, this study explores the effect of temperature on the electrochemical performance of Ipmc. The Ipmc started to lose functionality and displayed unpredictable performance for temperatures between 55 degrees Celsius. This might be due to the glass transition temperature of Ipmc starting at 50 degrees Celsius. At glass transition temperature, Napollon becomes rubbery, which affects the structure of the membrane and ion transportation. This is our future work to improve the electrochemical performance of Ipmcs. For instance, adding carbon nanotubes increases the surface area of the platinum electrodes, which increases the capacitance. We have here some references for this work, and here are acknowledgments. I just want to thank the Active Materials and Smart Living groups for their support for this work. I would also like to thank my support of NSF and SRNS for funding this work. Thank you.